So this is worksheet 1, electric force and electric field, pretty general stuff, just going over what we've already learned, especially in the first week. So let's just dive in with going over the useful formulas, starting with Coulomb's law. So I'm just going to move this down. And this is very standard equation. The only thing I want to point out is that K constant and then our Q1 and Q2 are within those absolute values, which means we always write them as positives. And that should be expected as, we never plug in the negatives there. So total electric force, that's just the summation of the forces present there. That's similar to 135A. Electric field, we'll use this in different cases, but notice the big Q. And we can also notice a relationship here with that force electric over Q equals the electric field. So just keep that in mind. There's some interconnectedness between these two concepts. And then I'm writing the kinematics equations just so we have them somewhere. They don't come back on this worksheet, but in the future they definitely will. And they are connected to these types of problems. The rule of thumb, I normally think of if there's time included in the question, start thinking kinematics if they're asking for some variables related to that. Okay, so I will just pause here for anybody copying. Few seconds. And if you guys have any questions, just speak up or drop it in the chat and I'll happily get that. Okay, and as I said, the key is already uploaded. So in case I move past a slide, just open up that drive and you'll see it. So here's our question 1. My thing's out of order. 3-point charges were given the values 65, 48, and -95 are placed in a single line. The center point is 0.35 meters away from each of the other 2-point charges. What is the electric force on the middle point charge? So standard approach to these kind of physics problems, we start by drawing the picture out. So here we have all 3 of those charges, starting with Q1, which is at 65 microcoulomb, and Q2, Q3. Notice with Q3 that there is the negative involved here. And next, we're looking for the electrical force acting on the middle point charge. That's this guy right here. So the force from charge 1, it's plus, goes away from plus, it moves the direction of positive with, and then goes towards minus. So arrow points away from this one and for F1 and towards Q3 for F3. So combined, we can see that both forces are pointing in the same direction. So as they have direction, that tells us they're a vector, and vectors by definition, you do not plug in the negative. Yeah, go ahead, Isabella.
Hi, sorry. Would it be possible to put this in present mode? It's a little bit hard for me to read.
Oh, apologies. If I do it in present, I can't really control this. Here, let me do this though. I can make it as big as I possibly can.
Okay, yeah, that's better already. Thank you so much.
Yeah. Sorry about. Thank you for letting me know. I just need to see that a little bit. Okay. So yeah, where was I? So yeah, we're dealing with vectors here. We never plug in the negative, and a vector has components. All right, and other thing we do here is we always want to write a coordinate system just so we have some standardization throughout this problem. Let's move on to next. So we're looking for the force acting on 2, and we know that that equals the first and third forces exhibited by these charges. Here, we're just going to use Coulomb's law and plug in the equation for both. How I like to think about it is the charge I'm at and what I'm interacting with. So Q1, and it's interacting with Q2. Similarly here, we have Q3, which is interacting with Q2. So that's how I know which Qs to pick. You notice that we're both talking or interacting with Q2, so that's what we're working with. If you have a good eye, we can just see how we can factor all this business out, leaving just Q1 plus Q3. And recall that we're not going to be plugging in the minus here because of those absolute values, or per the fact that when dealing with forces or fields, which are vectors, we never plug in the negatives. And then remember, vectors are opposed scalars, which we would have to recognize that negative. All right, so at this point, we're just plugging everything in, all those givens. Solve for F2, and that's what it comes out as. So that's the electric force on the middle point charge. that one pretty clear? Should be review. All right, I'll go ahead and go to the next one. And move this there. All right, so here we're going to be calculating the magnitude and direction of the net force and electric field on particle C due to the other two charges. So we're given this drawing. We know we're going to want to be looking at point C. That's what everything's going to be interacting with. And I just drew it up larger here. The other thing I did was just convert these centimeters to meters because these equations depend on that difference. So make sure you use meters. I drew my coordinate system and I have to draw my forces. So let's first start with the force that QA imposes on C. Same as plus charge, it points away. Here, this is a negative, points towards. The only difference between the last problem is now we have this force acting in 2 dimensions. There's a both Y component and an X component. So we're looking at the net force. Let's start with that, and we'll do electric field at the end. So what is that's like Pythag, and we should be very familiar with this from 135A, right? So we're looking for the net forces of C, and there is an X component and a Y component. Let's first start with the X component. So here we can see that the only force acting in the X direction is this FCB, and it is touching angle theta, so cosine. Sorry, I need to clear my throat. Excuse me. Yes, so it's touching angle right there, so cosine. And how do I know it's 30 degrees? And that's just my like knowing my trig and knowing with equilateral triangles, they're always going to be 60 degrees on the inside. This right here makes a 90-degree angle. 90 minus 60 equals 30. So that just kind of should be your sense. After which we're going to use the same equation like we did before, Coulomb's law, except we have to include that cosine theta, which recognizes it as the X component, solve out, and we get a value. Next, we're going to be looking at the Y component for the forces. Here we have an FCB Y component pointing upwards, and then the force by A, which is pointing downwards. As we've previously defined our coordinate system, Y pointing straight up, we can see that this FCB component corresponds with our positive direction, and FCA corresponds with the negative. Thereby, we're going to put a minus sign right here. After which, we're just going to solve very similarly to like as we would before. Just clean this up, factor this out. We see that actually all these Q's end up equaling each other because we only use the positive when dealing with forces and fields. So we can actually combine them into Q squared and then factor out Q squared, leaving sine theta minus 1 and the constant K and the R squared value provided. At this point, we just have to solve it, plug everything in. We're given the F net C. So at this point now we have the net forces X and net forces C. I'm sure you guys know what to do next. We just have to use Pythag to solve out the F net. All right. And we want to find that angle alpha. Just choose whichever trig function you want to run. I like using tan, and then just plug in what you need. And you just say 30 degrees below the positive X axis. If you were to plug in the negative here, because it did come out as a negative, you would end up getting minus 30. And that just tells you that 30 degrees below the positive X axis. So kind of a little point to make with forces and fields, vectors do not plug in the negative. However, if the answer comes out as a negative, you still need to recognize that as the negative, because just due to our coordinate system and how we define the problem, the actual forces induced by that, the net force on particle C is actually going down at that angle. Yeah, Iris, go ahead. Or sorry, Lily, go ahead.
Sorry, Iris is my twin. This is very confusing. Can you scroll up a tiny bit?
Oh yeah, sure.
Under where you wrote 1, I'm having a little bit of trouble seeing what the subscripts are. Does that just say F net C?
Yeah, F net X C. So F net in regard to X, and then for point C.
Okay, got it. Thank you.
Yeah. Okay, so this is a constant question I'd say to expect on exam. This type, probably more complicated. They'll probably give you a more like complicated triangle, probably not equilateral. So you need to be able to have a better trig intuition. But other than that, it's like this. Is there any other questions on this? Lily, do you still have your hand up, or is that from this? Okay. All right, I'm just going to move on ahead. Again, if you're still trying to copy down, Key's already posted. All right, so question 3. So this is very similar to a question we did in class previously. So point charge of 180 millicoulombs is located 40 centimeters to the left of a minus 20 millicoulomb point charge. Where is the electric field equal to 0? So let me zoom in first. And this is kind of our system here. So we have this 180, and then it's 40 centimeters to the left of this negative 20. So what we're looking for is, imagine if this is an infinitely long, I don't know, like very thin wire but has no effect on the charges. And we're looking where along that super long wire where the electric field equals 0. So how do we do that? We have to put in some scenarios. Let's start with scenario 1. I circled this right here, and that represents a position along that imaginary wire. And we treat it as a plus. That's kind of convention. So treat it as you would a plus charge. As a plus charge here, we can see that within Q1, it repels, so it will go leftwards. And since this is negative, it would go towards. But now looking at the actual quantitative evidence here, we have 180 and minus 20. 180 is so much bigger. That tells us that here they would not cancel each other out enough to equal 0, as 180 will kind of dominate in this scenario. In scenario 2, let's put it right next to each other. The plus on plus forces E1 to go that way, and then the negative, it goes towards Q2. Now these two vectors are adding on top of each other, so we know right off the bat, scenario 2, we can put a big X to that. It's not that. Now with scenario 3, though, we can see that, repulses by Q1 and towards Q2, but due to the proximity to Q2, that R squared value is actually smaller, and that smaller in denominator makes the bigger number by like division, by definition of division. And conversely, now that there's a larger distance right here, that 0.4 meters plus whatever the distance from here to here is, creates a smaller number. So this gives us an opportunity to cancel them out. Does that logic make sense? I know this is probably the most tricky part of this worksheet.
Wait, sorry, can you explain the reason why you did the 3 different scenarios again?
Yes. So we're looking for where along this super long wire, the electric field equals 0. I'm just going to start with the easiest one, and that's scenario 2. If we look at any position right here, we'll see that the vectors by the field add up to each other, and I'm going to say, even though they're both not the same, but they're double strong heading eastward, right? Both vectors are pointing eastward here. So we know that they will not cancel out. Nowhere along this part between them that the electric field by 1 and 2 would cancel out. With scenario 1, yes, there is now an opportunity to cancel out, but since the proximity to Q1 is so close, we know that R value, that R squared value, we're going to divide by, by like per our equation, we know that R squared value we're going to divide by is going to be small. So the product of that will be a larger number, and this value will not be able to compensate for that. The subtraction of E1 from E2 would not be able to compensate for this value for over here. And that kind of comes with me knowing how to do the problem and kind of having intuition. But if you were to plug and solve here, you would see that it would be impossible to prove. And then over here, per the logic of that R squared denominator, we can see that it will be E1 minus E2 would end up equaling 0. Does that make sense? And that's what I tried to say here. We know we work with this one. So this position is at the position at which electric field equals 0, as it's the E1 force goes to the field goes to the right here, and the E2 vector goes towards the left. And these are now able to cancel out. So only at this position, the electric field is equal to 0. Okay. So we're going to use our equation. And remember, this is that r squared value I'm talking about here. The bigger this value is, the smaller the E comes out as. So that's why when it's over here, it doesn't make sense versus over here. And we want the electric field net to equal 0. So thereby, we know the participating electric fields are E1 minus E2. We want that to equal to 0. We're going to use our equation, except here the r squared is that distance of 0.4 plus x. So 0.4 plus this distance x. And then the distance with respect to Q2 is just that distance x right there. At this point, we have minus and a 0, so we can move one to the other side, do some algebra just to clean this up, and we'll be able to isolate x. And that tells us the position at which the electric field equals to 0. And we write our coordinate system just so we know like what we're defining as plus and minus. E1's going in the same direction as our positive x, E2 is going against that. So E1 minus E2. And this, how I knew to do this is just we know we're solving for the case when the electric field equals to 0. Okay, so I think that's probably the most tricky one, but just looking at it, it probably makes it a lot clearer. All right, I'm going to move on to the next one. Let me just check to see if any questions. So in this question, we have a point charge. We're given a mass. Notice it's in grams. We need to convert that to kilograms to be able to appropriately use the equations. At the end of an insulating cord of length 55 centimeters, it is observed to be in equilibrium in a uniform horizontal electric field. When the pendulum position is shown, let me pull this down so you can see the picture, is shown with the charge 12 centimeters above the lowest vertical position. So right here, it's 12 centimeters above. If the field points to the right, determine the magnitude and sign of the point charge. So I just expanded this drawing right here to make it look a little bit clearer, and I drew in our key triangles. And right off the bat, we can answer the sign question. We know it's an equilibrium, I don't know if you can see the pen. We know that the object has kind of gone up and is stuck there in that equilibrium. As such, we know that the charge is plus as the field and force are pointing in the same direction. Had the force been pointing in the other direction, we would notice that the object would fling back, right? So as it's able to be held there, we know they're of the same, since field and force are in the same direction, we know it's plus. All right. Next thing I wanted to do was write in all my acting forces. So, we have the weight going down. Well, we'll start with, we'll know there's a weight. We have that electric force pointing towards the right, as we discussed, and we have this tension by this string that it's attached to. We're given the length of the string. We're given this height. So knowing that, we're able to break up this triangle to be able to find some angles. So we just do, 55 minus 12. That represents this part right here, where 12 is from this position to this position. That's equal to 43. And then use our good trig to solve for that angle. All right. Next, we move on to, and now we have obviously our components of tension, T cosine theta and then T sine theta, depending on where they are respect to that angle theta. Next, we're going to look at the summation of forces in the y direction. We have that T cosine theta pointing up and then mg pointing down. Just move the mass times gravity to the other side, divide by cosine, and you'll get a value. Next, when we're looking at the summation of forces in the x direction, we now have a value to plug in for T. We just got to express this F electric. That's an equation that we have on the first page, and divide by E on both sides. Remember, they gave us that electric field value. That kind of tips us off. We're going to be using this equation too, right? Because otherwise we'd been stuck. At which we just have to plug everything in, and we just work from there. And I just wanted to write a plus charge again, just to reiterate. All right, let me just zoom back out. And then before I pause the recording, I'm just going to do some quick announcements. So I already discussed to everybody in session, but I'm going to be using the Friday AM sessions to go over the homework that is either from before, even from the future, or the one that's due that night specifically. So if you need help with the homework or just want to check something, stop by there. Other than that, I'm going to stop the recording and see if there's any in-session questions. Thanks for watching, guys.